Hi everyone. In this video, I'm going to take you through a few questions to help us prepare for the January exam 2025. There are important concepts that we need to always remember as we do our revision. And so this is going to be done using these questions. So the first question, an ester X with the molecular formula C8H16O2 has the structure shown below. We have the ester, it has the ester link, the acid part, and the alcohol part, like we have indicated here. Right, so the first question, A, deduce the name of the alcohol used to synthesize X in a reaction with ethanoyl chloride. So we know this came from an acyl chloride and this other part came from an alcohol. Let us name the alcohol. We have the carbon number 1, 2, 3, 4, 5. So that is pentanol, but at carbon number 3, this is where the position of the functional group, the alcohol group, the OH group was at position number 3. That is where we are going to have 1, 2, 3, 4, 5 pentan 3-ol. This one we are guided by where the ester link is, so we know it is at position 3 that the OH was attached. Then there is a methyl group at the same position, and so the full name of the alcohol becomes 3-methyl pentan 3-ol. That is it. Done. All right, so we move to the other part. Over that. That is question B. One of the proton environments in X is labeled A, lowercase. We can see it, this one, the proton environment labeled A, this one, H3. So complete the labeling of this structure to show each of the other proton environments in X, clearly linking any that are the same. So we're supposed to look at the proton environment. That is the hydrogen environment where we have the carbon atom, according to carbon, the hydrogen atom, sorry for that, where we have the hydrogen atom, according to carbon. So we have the first one, A, which has been given to us. Then we have these methyl groups and these other methyl groups having the same environment, so they are going to show the same peak. So this is one other peak for the proton environment. The CH3 here and the CH3 here, they are similar, so they make one proton environment with 6 hydrogens. So that is B. We have C, another proton environment, CH2, CH2. The two are bonded to the same carbon, so they are the same. They are identical proton environment, and they are going to show the same area of peak. Then we have this CH3, which is bonded to a CO. In fact, this one a very unique one, which is even in a high resolution NMR, proton NMR, it is going to show a singlet, because it is bonded, it's adjacent carbon has no hydrogen. Very unique one. All right. So those are the proton environments that we were required to label. We move on to the other question, to the next question. After completing the labeling, we are going to describe 3 ways in which the high resolution NMR spectrum can be used to distinguish between the methyl groups of X other than A. All right. So we have the CH3-CH2 group will be at a chemical shift of 0 to 1.8 parts per million. And that is for this CH3-CH2 group. CH3-CH2 group, CH3 bonded to CH2, and this CH3 bonded to CH2 is the one. It's on an alkane chain. That's why it is on a lower value of the parts per million chemical shift. which is different from the CH3 of the bonded to the carbonyl group. Which other difference do we expect for the peak? The peak for CH3CO will be a singlet. That is what we have just said. Because the adjacent carbon has no hydrogen. Let's see that. This CH3 is bonded to the carbon that has no hydrogen. So this proton environment will have a peak, which is going to be a singlet, like we have stated, because the adjacent carbon has no hydrogen. And the peak for the methyl groups attached to the CH2 group will be triplet because the adjacent carbon has 2 hydrogen atoms. What do we mean by this? Let's see. The CH3 is bonded to a carbon having 2 hydrogens. So this CH3 and this one will have a triplet because the adjacent carbon has 2 hydrogen atoms, like we have indicated. And then the peak area for the methyl groups attached to the CH2 group will be twice the area for the methyl attached to the carbonyl. Let's see that. The methyl here and this methyl, that is a total of 6 hydrogen, 3 plus 3. That means the area will be bigger twice compared to the methyl that is bonded to the CO because this is just 3 hydrogens. That is why the area for these 2 methyl groups is going to be twice the area for this other proton environment. I think that is clear. We move on to the other part of the question. An isomer of X is a carboxylic acid with 5 peaks in carbon-13 NMR spectrum. Draw a possible skeletal structure for this carboxylic acid. A possible skeletal structure. Don't be skeletal. Shouldn't be a carboxylic acid. Should show 5 peaks in carbon-13 NMR spectrum. And so, look at the drawing we have made here. We should have 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. There is a hydrogen, a OH, and a O for the carboxylic acid part. Let's confirm whether this structure is going to have 5 peaks for carbon-13. So, for this carbon atom and this, those are 2 different carbon atoms. This one will have its own unique peak. This carbon will have its own unique peak. This carbon and this carbon are similar. They are bonded to a carbon with 1 hydrogen here, and the 2 are also bonded to a CH2. So these 2 carbons have this identical peak, have the same peak because they are similar in terms of environment. Then this carbon, which is a CH2, and this carbon, which is a CH2, which is bonded to 2 hydrogen, the 2 have similar environment again, so they are going to show the same peak. And finally, the CH3 here and the CH3 here are similar, so they are also going to show identical, the same peak. So when we count these 2 CH3, that is 1 peak. This C2 and this one, another peak, those are 2. This C2 and this C2, another peak, those are 3. This carbon, another peak, those are 4. And this carbon, another peak, those are 5. Done. We move on to the other question, part D of the question, a simple question down here. The painkiller aspirin is also an ester formed by the reaction of 2-hydroxybenzoic acid and ethanoic anhydride. I see we have the aspirin here. part of the mechanism for this reaction is shown. So we have the mechanism for the reaction shown. The mechanism for the reaction is down here. We are supposed to add a single curly arrow to step 1 and a single curly arrow to step 2 to complete this part of the mechanism, which is well done. The lone pair on the oxygen of the carbonyl attacking the hydrogen ion, so that we're able to form the protonated carbonyl, and then we are going to have the lone pair of the OH group attacking the partially positive carbon, and this is going to neutralize the positive change here, because a pair in the double bond is going to move to the oxygen atom. So this is the arrow that is required, and the other arrow required are shown. Nice. Then set the role of the hydrogen ion in the synthesis of aspirin. The role of the hydrogen ion is going to be a catalyst. It is acting as a catalyst, which is only providing an alternative route with a low activation energy, and that is why it is going to be regenerated at the end of the reaction. So we move to question 2. This question is about acids containing sulfur. Sulfuric acid react with the sodium hydroxide solution as shown. So we have the equation for the reaction between sodium hydroxide and sulfuric acid. Calculate the pH of the solution formed when 20 centimeters cubed of sulfuric acid of concentration 0.0720 moles per dm cubed is mixed with 80 centimeters cubed of sodium hydroxide solution of concentration 0.240 moles per dm cubed. So we are supposed to give our answer to 1 decimal place. So let's see how we should do that. So we are supposed to first of all calculate the moles of the sodium hydroxide, 0.240 moles in 1,000. Where do we get that? We have the concentration. We need to understand how to interpret the concentration without necessarily just going direct to the formula of calculating the number of moles. We need to understand what concentration actually means. So if we are given here 0.240 moles per dm cubed, this actually means that in every 1 dm cubed, there is 0.240 moles, which we can write as 0.240 moles is in 1,000. 1,000 is 1,000 centimeters cubed is the same as 1 dm cubed. And we want to know the moles in the 80 centimeters cubed of solution of sodium hydroxide that was used in this particular experiment. And we have been able to get the moles, which is 0.0192. We move to the moles of the sulfuric acid. We do the same. We have been given the concentration of the sulfuric acid here. So we are going to have 0.0720 moles in 1,000 to interpret the concentration. And we want to get the number of moles in 20 centimeters cubed. So we have 0.0720 moles. We multiply by 20, divide that by 1,000, we get the number of moles of the sulfuric acid. After getting the moles of the two substances, we need to know the mole ratio. This 1:2. This helps us to know which substance is actually 0.0192 moles. When we minus what is required, we get what is going to remain for the base, 0.1632 moles of the base. The 0.00144 moles of the acid that we got will only take 0.0288 moles of the base. And after taking 0.00 8 moles of the base, 0.01632 will remain. So we want to use this to know what is the concentration of the hydroxide ions remaining after the neutralization. And when we know the concentration of the hydroxide ions, we know the concentration of hydrogen ions using the ionic product of water. Remember, after mixing a volume of 20 centimeters cubed and 80 centimeters cubed, now we got a new total volume, which is 100 centimeters cubed. So, having the moles of the base now in the solution after the reaction, which is 0.01632 moles, is in 100 centimeters cubed that we have now, we can get the concentration. What do we mean? We can get the amount of moles in 1,000 centimeters cubed, or in a liter, or in 1 decimeters cubed, which is simply going to be done by we multiply those moles by 1,000, we divide by 100, we get the concentration of the hydroxide ions in the solution in 100 centimeters cubed of solution. After getting the concentration, which is 0.632 moles per dm cubed of the hydroxide ions, we can now get the concentration of the hydrogen ions by defining the ionic product of water by the amount of moles of the hydroxide ions that we acquired. We get the concentration of the hydrogen ions as 6 point, we can see we are going to get 6.1275 times 10 to the power negative 14. And since we know the formula for pH, pH is supposed to be negative, the logarithm of the concentration of hydrogen ion, which we get as 13.2. That is the pH of the solution or of the mixture that we have. The pH of the mixture, the pH of the solution we have formed, where we have the sodium hydroxide in excess. So we have the sulfurous acid. This is the next question, question B. Sulfurous acid is a weak acid and dissociates as shown, H2SO4. We have hydrogen sulfate and hydrogen ion. It forms a buffer solution when mixed with sodium hydrogen sulfate. That's what is meant by the term weak in this context. We know what a weak acid is or what a weak base is. So weak here in connection to weak acid is the one that dissociate or ionizes partially in solution, giving a low concentration, but we're not interested in the concentration. We actually, what is the meaning of weak partially dissociating solution? That's what is meant by the term buffer solution. That is Roman 2 of part B. What's a buffer solution? These are the direct questions that we ensure that we must get them right. They are definition questions which we can get directly from the textbooks or research or notes can give us this. So any direct question, what is the meaning of a weak acid? What's the meaning of a weak base? What's the meaning of a buffer solution? They are some of the questions we must ensure that we get those marks. We don't lose those marks. A solution that resists change in pH when small amount of acid are added, or when small amount of base are added. Roman 3 of the question, we are going to calculate the mass of sodium hydrogen sulfate that should be added to 50 centimeters cubed of 0.0480 moles per dm cubed sulfurous acid solution to form a buffer solution of pH 2.1. Nice. We have the Ka of the sulfurous acid given to us, 1.54 times 10 to the power negative 2 moles per dm cubed. And we have the relative formula mass of the sodium hydrogen sulfate given to us as 104.1. How do we go about this question? We have the pH given to us. The pH is 2.18. This helps us to know the concentration of the hydrogen ion, which is going to be equal to 10 simply to the power negative 2.18. We get the concentration of the hydrogen ions. But we have the equation that links the Ka value, the concentration of the acid and the salt, and the concentration of the hydrogen ions from this. The concentration of hydrogen ion is equals to the Ka times the concentration of the acid over the concentration of the salt. And this simply, if we make Ka the subject, it means the concentration of hydrogen ions times the concentration of the salt divided by the concentration of the acid to get Ka. And since we have Ka as 1.54 times 10 to the power negative 2 equals to 6.6069 times 10 to the power negative 3 times the concentration of our salt sodium hydrogen sulfate defined by the concentration of the acid that was given to us. The concentration of the acid 0.048. We can make the concentration of the salt, the sodium hydrogen sulfate, the subject of the formula. We have 1.54 times 10 to the power negative 2, which was our Ka, times the concentration of the acid, which was 0.048. We defined that by the concentration of the hydrogen ions, which we had got 6.6069 times 10 to the power negative 3. This is going to give us 0.11188 moles. Right. After getting the concentration of the salt, what was the question? Let's come back to the question here. Remind ourselves, calculate the mass of sodium hydrogen sulfide that should be added to 50 centimeters cubed of 0.0480 moles per dm cubed sulfurous acid solution to form this buffer. So our interest is not the concentration but the mass. So what do we do next? We need to use the concentration and the volume we have to get the moles. We know what this means. This is the concentration in 1,000, about 50. The volume was 50 from the question. We can see we have 50 as the volume. So we can use the volume and the concentration we defined. We are going to get, that is the moles, that concentration times. So we have the moles 0.11188 times 50, the volume defined by 1,000. So moles will get the concentration times the volume. So we have the moles 5.5941 times 10 to the power negative 3 moles. So after getting the moles, we can get the mass, because we know mass is just the moles we have times the molar mass. Since molar mass is mass for 1 mole, so this moles we multiply by the molar mass, we get the mass. So mass is going to be 0.58235. Yeah, 0.58235. Done. We've got the concentration. We've got the mass of the sodium hydrogen sulfide. All right. Question number 3. This question is about carbonyl compounds such as ethanol. Ethanol is an aldehyde. Ethanol reacts with weak acid hydrogen cyanide to form a racemic mixture of hydroxynitride. A small amount of sodium hydroxide solution is also added to the reaction mixture. Complete the mechanism for the reaction, include curly arrows, the structure of the intermediate, and any relevant lone pairs and dipolars. All right, let's see. We have the aldehyde here, the ethanol. You're supposed to complete the mechanism. We have used our green and yellow colors here to show the mechanism, how it is going to be complete. You know that cyanide ion is a nucleophile. It has got a lone pair of electrons, which we must show this lone pair of electrons. So we have the lone pair of electrons here. We have the partial changes on the oxygen side of the carbonyl is supposed to be partially negative, delta negative, partially positive, delta positive for the carbon. So we're supposed to show a curly arrow from the lone pair of the cyanide ion all the way to the carbon. Make sure the direction is correct to the carbon. Then we are going to have another curly arrow here from the board, the double bond of the C and O of the carbonyl to the O. so that our intermediate is going to have the O that is negative and it has lone pairs. And the lone pair of the O will be used to make a covalent bond with the hydrogen from the hydrogen cyanide. So we need another curly arrow from the lone pair of this oxygen in the intermediate all the way to the hydrogen. And we need another curly arrow from the bond between hydrogen and the cyanide. And that is what is eventually going to give us the product down here, which is our 2 hydroxypropanitrile. 3 carbons, 2 hydroxypropanitrile. That is going to be our product. All right. Explain why. So we have the next question. Explain why a small amount of sodium hydroxide solution is added to the reaction mixture by considering the nature of the attacking species in the slow step. We need to remember which slow step is and what it is going to form. Our slow step is involving the cyanide ion, which attacks the carbon partially positive, and we are able to get this intermediate here. So we are adding sodium hydroxide so that the sodium hydroxide can react with the hydrogen cyanide. We get the hydrogen part reacting with the hydroxide, and once it reacts with the hydrogen cyanide, the equilibrium moves to the right and the concentration of the hydrogen increases. We can make the intermediate hydrogen cyanide react. All right. Question part B. Reduce the rate equation for the reaction using the mechanism. So our mechanism is affected by both the cyanide and the aldehyde. So from that we can see our rate equation is going to be K, the ethanol and the cyanide. Each of them has order with respect to the substances. So we are trying to sketch on the axis to show how the concentration of ethanol affect the rate of reaction. We already know that it is supposed to be a straight line because this is rate against concentration. As the concentration of ethanol increases, the rate increases, and the reaction is first order with respect to the ethanol. That's why it is a straight line from the origin. All right, we move on to the next part. Part D. Let's see. Nice question. Carbonyl compounds can be identified from their 2,4-dinitrophenylhydrazine derivatives. Describe this process, including in your answer observations you would see in the formation of the 2,4-dinitrophenylhydrazine derivative. An outline of the steps used to separate and purify the derivative, giving the purpose of each step, how the derivative is used to identify the original carbonyl compound. Detailed descriptions of practical techniques are not required. You have the instructions. Let's go. You want to identify the carbonyl compounds using what? The derivative formed. For us to form the derivative, the 2,4-dinitrophenylhydrazine derivative, we use the 2,4-dinitrophenylhydrazine as the reagent to test for the presence of the carbonyl. Now that we know this is a carbonyl, we don't know whether this carbonyl is an aldehyde or a ketone. We can test first of all that this is a carbonyl by adding 2,4-dinitrophenylhydrazine. So when we add 2,4-dinitrophenylhydrazine to the carbonyl, we get an orange precipitate. Some books will say a deep orange precipitate. And it is formed when the 2,4-DNPH or dinitrophenylhydrazine is added to the carbonyl compound. All right, we don't know what this carbonyl compound is. Is it an aldehyde? Is it a ketone? So what do we do? The precipitate we obtain can be filtered. So we filter it And after filtering the precipitate, we dissolve it in boiling solvent. We choose a solvent and then we allow it to cool to form crystals. So then the crystals are filtered and rinsed with ice-cold solvent in order to remove any dissolved impurities. After removing the impurities, we get the crystals, we dry them between filter papers to remove the solvent, and we can identify the crystals by identifying or determining the melting temperature. And whatever the melting temperature we get, we compare with data booklet volume. And this is going to help us to know that this is this derivative, and if this is the derivative, it was obtained from this particular aldehyde or this particular ketone. Nice. All right, we move on to the next question. Question number 4. Let's see question number 4. What does the examiner want us to understand before Unit 4 exam chemistry come January 2025? This question is about the hydrolysis of halogen alkanes with hydroxide ions. The initial rate for the hydrolysis of 2-bromobutane, we have 2-bromobutane here, were obtained from different initial concentrations of the reactant. Both 2-bromobutane and the product formed in this reaction exist as pairs of stereoisomers. Nice. Bromobutane and the product, stereoisomer. So we have 2-bromobutane reacting with hydroxide ion. This could be coming from sodium hydroxide, potassium hydroxide, hydrolysis of halogen alkanes. We get an alcohol and bromide ions that have been substituted, nucleophilic substitution. All right, we have a table. What is the table showing us? Let's see the table. We have a table having 3 experiments. We have the concentration of 2-bromobutane, initial concentration of the hydroxide. We have the rate, the initial rate. All rates are determined at the same temperature. That's what is meant by the term stereoisomer. What did we say? We think that we should not lose this mark of direct questions from our textbooks or research notes, where we only need to know to define. These are isomers that have the same structural formula but different spatial arrangement of atoms. Yes, arrangement of atoms in space is different. They are just similar, just the arrangement. All right. Shows that the data in the table are consistent with the SN2 mechanism for hydrolysis of 2-bromobutane. All right, let's see, SN2. SN2, it means now that this 2 tells us that there are 2 species involved in the rate determining step, meaning the 2 substances, that is hydroxide ion and 2-bromobutane, should be affecting the rate. Right, let's see. If it shouldn't be affecting the rate, if you look at the experiment 1 and 2, we can see that doubling the concentration of 2-bromobutane, the rate also doubles. Let's see. From experiment 1 and 2, why am I choosing experiment 1 and 2? Because at that time, the hydroxide ion's concentration is constant. So I'm only changing the concentration of 2-bromobutane. And when we double it, the rate doubles. 0.027 times 2, 0.05. Oh, all right. So automatically, the reaction is faster with respect to 2-bromobutane. Let's see about hydroxide ion. For the hydroxide ion, if I just choose experiment 2 and 3, what is happening? If the concentration of 2-bromobutane is multiplied by 1.5, the rate should be multiplied by 1.5. But unfortunately, when we multiply 0.054 by 1.5, we don't get 0.162, we get 0.081. So what has happened? That means automatically that the hydroxide ion must also be affecting the reaction. So concentration of 2-bromobutane has been multiplied by 1.5. the concentration of hydroxide ion has been multiplied by 2. And the concentration and the rate has been multiplied by 1.5 and then multiplied by 2. Wow. What does that mean? If I take the rate that was being obtained when we multiplied the rate by 1.5, we take the rate that we are observing here, divide the 2, we get 2. And the concentration of hydroxide ion has been multiplied by 2. 2 to power x, 2 to power 1, x equals to 1. First order with respect to hydroxide ions. Nice. So this means that first order with respect to 2-bromobutane, and for experiment 2 and 3, the concentration of 2-bromobutane increases by a factor of 1.5 and the rate triples as the hydroxide ion doubles. Therefore, first order with respect to hydroxide ions. Yes. That's why we have 1.5 times 2. That is 0.054 times 3. We get the concentration, the rate. We get the rate affected by both hydroxide ions and 2-bromobutane. Lesson 2. Next question. In one experiment, a single stereoisomer of 2-bromobutane was hydrolyzed. Explain the stereochemistry of the product of this reaction. A single stereoisomer of 2-bromobutane. A single stereoisomer of 2-bromobutane hydrolyzed. That means the hydroxide ion attached the carbon that is partially positive in the opposite side of the bromine atom, since the bromine atom is large. And that means you're going to have a single product, and this product is going to be optically active because it is able to rotate in the opposite direction. The reactant. Okay, part B of question 4 we have 2-bromo-2-methylbutane can also be hydrolyzed with hydroxide ions. The mechanism for the reaction is SN1. The reaction profile is shown. So we have a reaction progress of reaction. You have to pick here, we have the reactants and the products. So what I will do? Explain how all the features of this reaction profile are consistent with an SN1 mechanism. What do we see in this graph? There are two activation energies profiled as two peaks. The other peak, and this indicates that there are two steps that are involved and eventually an intermediate formed. So the first activation energy is this one. You can see it is higher. The first activation here, the first one here is higher than the second one, and therefore you can see that the first step is the slower step. The slower step, the rate determining step. One step is involved in the rate determining step. One species is in rate determining step, and that is why it is SN1. Right? So we move to question 5. Question 5, what we have? So this question is about group 2 carbonates. Barium carbonate decomposes at high temperatures as shown. Carbonates composed, we get barium oxide and carbon dioxide gas. So calculate the standard entropy change for the system. Standard entropy change for the system. The standard entropy change for the system, you have to know the products and the reactant that you can go get the entropy of the. So what do the product is barium oxide and carbon dioxide. So we have 70.4 plus 213.6. Here we have it. We minus the reactant, the entropy of the reactant, and the reactant here is our barium carbonate, which has a standard entropy, molar entropy of 112.1. All right, and that gives us 171.9 joules per Kelvin per mole system. The lowest temperature at which barium carbonate decomposes is 712. The mean temperature. So we use this information and your answer from A1 up to calculate the standard enthalpy change of the reaction in kilojoules per mole. We are trying to give our answer to an appropriate number of figures. So one thing that we need to remember is that at minimum temperature, that is when the reaction is going to be feasible. The reaction is, so the S total is supposed to be the minimum value S total can now for the reaction to be feasible. That is when S total is 0. And that time it means the entropy of the surrounding is going to be equal to negative the entropy of the system. Remembering that when we add surrounding and system, we get S total. So that means we can use the S of the system, the entropy of the system that we have got here, and the formula for the entropy of the surrounding to be able to get the enthalpy change of the reaction. What does that mean? If we take the entropy of the system that you have calculated here, 171.9, we define by 1,000 to change to kilojoules per Kelvin per mole, then we can use it and the formula for the entropy of the surrounding in order to get the temperature, in order to get the enthalpy change, because the temperature is already given to us. That is the minimum temperature required. So when we equate the entropy of the surrounding, which is negative 0.1719 kilojoules per Kelvin per mole, is equals to the enthalpy negative divided by temperature. You can cross multiply and make T the subject of the formula. And converting the temperature to Kelvin, we are going to have 985 multiplied by the entropy of the surrounding is negative 0.179, and we get the delta H here. Take it back. We define by the negative sign on both sides. Let's multiply with T. Then we are left with delta H. So we have delta H equals to 0.179 divided by 985. The enthalpy to be positive 160. Right, part B. Magnesium chloride is used in the manufacture of tofu from soya milk. An experiment was carried out to determine the enthalpy change of solution of anhydrous magnesium chloride. 4.26 grams of anhydrous magnesium chloride was added to 200 centimeters cubed of ionized water in a polystyrene cup. The mixture was stirred to ensure all the solid dissolved to form a solution. The temperature of the solution rose by 6.8 degrees Celsius. Then we are required to calculate the enthalpy change of solution. Delta H of solution of anhydrous magnesium chloride. Include a sign and unit to the answer. The specific capacity of the solution is 4.18 joules per grams per degrees Celsius. So we need to calculate Q, or the energy released, using the formula MC delta T. And our value is supposed to be negative now that we know that the temperature rose. So we know energy was lost to the surrounding. That is why the temperature rose, hindering that our thermometer part of the surrounding. That. So we have 200, which is the mass, the volume that was used, assuming that you are using the density of water, 1 gram per centimeter cubed. The mass becomes 200 grams multiplied by the specific heat capacity, which is 4.18, multiplied by the rise in temperature, which is 6.8. This gives us 5,684.8 joules. Let's get the number of moles of the magnesium chloride anhydrous. We already have the molar mass 95.3, and we know molar mass, that is the mass for 1 mole. We have a mass of 4.6. So when we define the mass defined by the molar mass, we get the moles of the magnesium chloride. So these moles are the ones that make the solution to produce an energy of 5,684.8 joules, or about 1 mole, going to the molar enthalpy change of solution. So when we define the heat energy, the energy released defined by the number of moles, we get the energy in joules per mole, which you can divide by 1,000. Appropriate number of significant figures, we can do the significant figures. This gives us 127.17, which is negative 127 kilojoules per mole negative. It's exothermic. The dissolving of magnesium chloride thermic. Temperature has gone up when it is dissolved. Right. It's negative 1.7 kilojoules per mole. Nice. Okay. Part C of the question. The standard enthalpy change of solution delta, which of theta of solution of anhydrous magnesium chloride, can also be determined using a cycle. Complete the S cycle shown by adding appropriate formula with the state symbols to the empty boxes. So we have magnesium ions in gaseous form, chloride ions in gaseous form. That's the first part that we need to fill. Then we will get magnesium chloride in solution in solid form, the ionic compound. All right, given that the lattice energy is negative 252,526 kilojoules per mole, and the standard enthalpy change of hydration of magnesium chloride is negative 1,920 kilojoules per mole. Right. So we're going to let the enthalpy change of hydration of the chloride ions to be X, because the question that we're supposed to answer to calculate the standard enthalpy change of hydration of chloride ions using the cycle, the data in C, and the answer we got in B. All right. So we have the cycle here. We've already let the enthalpy change of chloride ions, enthalpy change of hydration of chloride ions to be X, 2 moles of that, because X is the molar enthalpy change, 2 moles of that is going to be 2X. Then we have the lattice energy given to us, so negative 2,526. We have the standard enthalpy change of solution of magnesium chloride given to us, negative 127. That is what we obtained in part B of the question. All right, and the standard enthalpy change of hydration of magnesium ion is negative 1,900. So we are going to use the cycle and move through my finger arrow here, or go direct from the magnesium ions, chloride ions, to the same ions in solution form from the ions in gaseous form. So when we equate the two signs, we are going to have negative 1,020 plus the 2x for the chloride being equals to the lattice enthalpy, which was supposed to be negative 2,526 plus the negative 127, which was the enthalpy change of solution. All right. So if we make 2x the subject of the formula and eventually x the subject of the formula, we are going to have x, which is the enthalpy change of hydration of chloride ions, being 306.5. This is okay. negative. That's there as if value. So that's correct. So let's come to the part D. Theoretical lattice energy from a Laurent is negative 2,326 joules per mole. If two assumptions used in theoretical calculation, that is energies. Theoretically, we have to assume that this compound is 100% ionic and the ions are perfect spheres, not covalent. The points such as the changes are point changes and the ions are in contact with each other. Theoretically, those are the examples. There is part 2 of question part D. Explain the difference between the theoretical and the experimental values for the lattice energy of magnesium chloride. Explain the difference between the theoretical and experimental values for the lattice energy of magnesium chloride. So, the experimental value is more exothermic. This is because the chloride ion is polarized by the magnesium ion, the cation magnesium ion, and that makes the bonding in chlorine to have some covalent. There is bigger overlap, there is stronger attraction, so more energy is released when you're breaking the bond. That is exothermic. Alright, we move to part E of the question. Hydrated barium chloride is a soluble toxic salt. It can be formed from the reaction of barium carbonate with hydrochloric acid as shown. So a 5.00 gram sample of barium carbonate reacted with 120 centimeters cubed of 0.5 moles per dm cubed hydrochloric acid. So part 1, show that the hydrochloric acid is in excess in reaction. Sorry for the do it. Sorry. Alright. Show that the hydrochloric acid is in excess in this reaction. Sure. We have barium carbonate. We want to get the moles of the barium carbonate since we know using 5 gram sample. Know that 1 mole of barium carbonate is 197.3, that is a molar mass, or the relative formula mass. And therefore, we can use it to get the moles of the 5 grams. 5 grams divided by the molar mass, we get the moles of the barium carbonate. After getting the moles of the barium carbonate, we also need to know the moles of this hydrochloric acid, the 120 centimeters cubed of 0.1 mole per dm cubed concentration hydrochloric acid, and we get the moles of the hydrochloric acid. So we have 0.06 of hydrochloric acid and we have 0.0534 moles of barium carbonate. From the reaction, we know that the mole ratio is 1:2 for barium carbonate is to hydrochloric acid. So, if I have calculated the moles of the acid at 0.06 moles, how many moles of barium carbonate do I need to use to react to the 0.06 moles? I need 0.03 moles. What did I use? 0.03 moles? Oh, look at what I used. I used 0.02534, which is less than what I need. Meaning this hydrochloric acid, 0.06 moles of hydrochloric acid that I'm using is excess. If I was to use it, then I need 0.03, but I don't have 0.03 moles of barium carbonate. I only have 0.025. So I need something less than 0.06. That is what we are saying. Since the 0.025342 moles of barium carbonate used is less than what is required to completely react to the 0.06 and what is required is 0.02, therefore the hydrochloric acid. Done. Alright, Roman 2, sorry. All of the barium carbonate reacted and produced 6.19 grams of hydrated barium chloride. All of the barium carbonate. That was the 5 grams. Calculate the relative formula mass of the hydrated barium chloride. and we deduce the formula of N, the value of N. So we produced 6.9 grams of the barium chloride, and we used 5 grams, which was equivalent to 0.02534 moles of barium carbonate. This is obviously our limiting reagent, since we already concluded that the hydrochloric acid was processed. And because the mole ratio of the barium carbonate and the barium chloride is 1:1, we will produce the same number of moles of barium chloride as barium carbonate. So we will get 0.02534 moles of barium chloride in our reaction. Once we get that, and we know these moles that we are producing here, the moles that you're producing here, the moles that you're producing here of barium chloride has the mass that we have been given here, and therefore we can say these moles of this mass are about 1 mole. To get the molar mass, we get the molar mass of 244.26. After getting the molar mass, we can make an equation to get the value of this N, the number of moles of the water of crystallization. We know that water is 18, that's the molar mass or the formula mass. So when we know that water is 18, we can just calculate using the formula. So we have what? We have 137.3, that is the atomic mass for barium. Chlorine, that 5.5 times 271 plus water is 18 times N, 18N. We equate to the molar mass that we obtained here. Here. Yeah, we have this. This is the molar mass that we obtained, 244.26. So we come and equate it, then we make N the subject, and eventually we get the N value. You can see the N value. N is equals to 2, 1.998, approximately equals to 2. N is equals to 2. Thank you for watching.